So today we're going to talk about CERN and how CERN manages GPUs. My name is Dana, and I am a computing engineer at CERN. But also I've done a lot of work on using GPUs on Kubernetes, sharing GPUs on Kubernetes, and also different types of benchmarking, and in general, different topics around the same area. So to start with, what exactly is CERN? Well, CERN is the European Organization for Nuclear Research. It operates the largest particle collider in the world, which is called LHC, or Large Hadron Collider. It's a tunnel, 100 meters underground and 27 kilometers long, where scientists accelerate particles to close to the speed of light and make them collide at 4 locations along this ring. This is where we have our detectors that are called CMS, LHCb, Atlas, and ALICE. When particles collide, a lot of information is being created, and we cannot store all this information. So as a result, we need to filter. So some of information will go in our data center for further studies, but a lot of it will be discarded. And to do this, we have systems in place that are called triggers. And you can have triggers at different levels. 1, when it's closer to the collision site, and then 2 and 3. So this is LHC. This is where we have our detectors. And this is how a collision looks like inside one of the detectors. And there is a collision every 25 nanoseconds. This is trigger level 1 that does a lot of discarding of the data, and trigger level 2 and 3. After this, information goes to be stored on our data center. As well, we have 1 copy of the data that goes on tape for long-term storage. And if you want to find more about CERN, please visit the awesome video I linked on the slide. All right, so with this out of question, so why does CERN need GPUs? And to show you why, I pasted a screenshot from Inspire Hub, which is a trusted community hub where scientists can share and find accurate scholarly information. And you can see that the interest in using GPUs among scientists just skyrocketed in the last years. And here you can see just a couple of examples how scientists are trying to make use of GPUs in the area of particle accelerators. So what often happens is that scientists have access to CPUs because they're easier to get and they're less expensive, and they run simulations on CPUs. But at some point, because of the discussions in the industry, they start considering the benefits on running on GPUs instead. So they start summarizing their use case, and they formally ask to get access to 1 or more GPUs. And if they're lucky, they get access to at least 1. Once they get access, they have to do a lot of iterative work to make their script work on GPUs instead of CPUs, which results in a lot of idle time. Also, even when the script is ready, you still can have a lot of idle time between the runs. So what can we do about it? GPUs are expensive, and idle time is just unacceptable in this case. Well, what we decided to do about it, we decided to have a single point of GPU access. And what this means, it means that we are trying to centralize all our GPUs into a common pool. And then when a user needs a GPU, they will go to this single point of access, request the GPU for their specific needs, be it simulations, inference, CI runners with GPUs, training, or anything else you can think of. You go here, you get the GPU for a limited amount of time to run your workload, but once you're done, you release it back to the pool so that other users can take advantage of it. And this is how it looks like. So we have our users, we have our GPUs, and users go on the GPUs when they are available. Once they're done, they release the GPU, and others can go there. And of course, this works great when you have more GPUs than users. But we all know this is not the reality we live in. And at some point, we start having users that are waiting for a very long time to get access to a GPU. And this results in just angry users that have been waiting for days to get access, and they still cannot manage to. And sometimes they leave. All right, so from one point of view, GPUs are always in use now. You can see that they're almost always red, so they're allocated to someone, which is great. But at the same time, are the actual GPUs used? And what we noticed from our monitoring is that sometimes users just try to get a GPU and don't do anything on them, or they run their workload, but their workload uses like 25% of what the GPU can do, 50%. But anyway, you still have a lot of idle resources. And this is where GPU sharing comes into play. And there are multiple ways of doing GPU sharing, and the first one we're going to consider is time slicing. So with time slicing, the scheduler gives an equal share of time to every process that is scheduled to run on this GPU. As you can see in the image I posted, the compute is given to one process at a time, and then there is a context switching, and then all of them are alternating. At the same time, the memory is assigned to one process at a time. And this is because doing a context switching with the memory would be extremely costly, so this is not something feasible. To enable time slicing when you're using Kubernetes and GPU operator, it's very easy. You start with your node that already is advertising at least one GPU that is available to be used. And then you can go to the configuration of your device plugin and say that you want to get access to the GPUs, but with sharing, and in this case, time slicing. And I'm requesting, on this example, 4 replicas. So I'm going to time slice my GPU between 4 processes at the same time. To actually use this configuration, I have to go ahead and label the node where I have a GPU with the configuration that I called in this case slice 4. Once I do this, in a couple of seconds, you'll see that your node starts advertising the shared GPU instead of the full one. And then you can proceed and actually schedule work on this GPU by creating, in this case, a pod that is requesting access to the GPU using spec, containers, resources, limits, which is nothing new. The advantages of time slicing is that it works on a wide range of NVIDIA architectures. It's easy to set up, and in theory, you could have an unlimited number of partitions. The disadvantages is that you don't have memory isolation. So basically, one process could starve another. And also, you cannot set priorities. So you cannot say, this process is more important than the other one, so please, if there is any kind of contention, evict this one, but keep the other one running, which makes it inappropriate for anything that is latency sensitive. And to exemplify a bit more details how this would work on a real-life example, I'm going to introduce a couple of use cases. So in here, I think the code is not very important. The important part is the GPU consumption behavior. So first of all, our first use case is a badly coded simulation job. So we have a long-running process that consumes just a little bit of our compute, but is running for a long time, and you cannot really do anything about it. Secondly, we have an inference service that is only sometimes triggered by outside events. So we don't know exactly when it's going to run, but we know it runs from time to time, and when it does, it consumes a lot of the compute that is available on the GPU. Lastly, we have a notebook user. We have absolutely no idea what to expect here. We could have memory leaks. We could have bad considered batch sizes. We could have memory which is just logged by an idle notebook. Absolutely no idea. And we're going to run all of them on an A100 GPU. So we start with use case number 1. And we take a look at our monitoring. What you can immediately notice is that the GPU is severely underutilized. So in this case, we have around 20% of memory utilization and some utilization of the compute, but a lot of resources are just staying idle. And to improve this a little bit, we're going to try to onboard use case number 1 and use case number 2 on the same GPU with time slicing. So you can see where 1 was running, and then we have also the spikes from when use case number 2 is triggered. And we can immediately see that we are getting to better memory consumption, around 50%. And also, we're getting spots where the GPU utilization is 100%. So we're doing much better, but still, we can do even better than this. So we're going to risk and onboard use case number 1, 2, and 3 on the same GPU with time slicing. And we'll see what's going to happen. So again, you can see where 1 was running. We can see the spikes from 2. And now the memory is going up. This is when use case number 3 started running. And we can see that we're getting to 100% GPU utilization. So this is perfect. This is exactly what we wanted, right? No, not really. Because what happened in reality is just use case number 1 and 2 were starved for use case number 3, that was just trying to consume more and more and more memory. And you can see the drop in the memory. This is when 1 and 2 stopped running. And the way I like to think about it is that a GPU is a full, big, fancy boat. And we have our use case number 3 enjoying this boat on its own, while use case 1 and 2 were evicted and left to drown, unfortunately. Enjoying the beautiful day in the mountains. All right, so let's consider other ways of doing sharing then. Another one is multi-process service, or MPS. And MPS is a runtime architecture that allows you to do cooperative multi-process CUDA applications. The big difference here is that, also you can see in the image, we don't have the context switching anymore. So all the processes are running on the GPU at the same time, all the time. Also, you get an additional process on your GPU, which is called the MPS server, which has to manage the amount of memory and compute that is allowed to be consumed by every client. So in theory, this is already an improvement from time slicing. To enable MPS is extremely similar to time slicing. Again, you have the device plugin. It's just instead of sharing with time slicing, you're going to share with MPS. Again, you go ahead, you label your node, and eventually in a couple of seconds, you'll see that your node starts advertising the shared resource instead of the full GPU. In terms of advantages, you don't need to do context switching anymore. It's easy to set up, and it works on a wide range of architectures. In terms of disadvantages, you still have memory isolation limitations. It's hard to monitor per process, and some resources need to be wasted in a way to manage the amount of memory and compute that is allowed to be used by processes. And lastly, we're going to dig into MIG, or multi-process GPU, multi-instance GPU. So MIG is a way to partition your GPU at the hardware level. So now you can think of every partition like a small GPU. Processes cannot influence each other anymore. Each of them have their own isolated high bandwidth memory, they have their cache, their compute cores, and you have quality of service in this case. You know exactly how much you can expect. One thing that you have to consider, though, is that you cannot just partition your GPU into random instances. You have to follow the structure you see on the table, and you need to make sure that when you sum up all your instances, you get back to what you started with. A full GPU can be thought of as an abstraction of memory units and compute units. And you have 8 memory units in the beginning and 7 compute units. So whatever the partition you choose is, just make sure you're not wasting any resources. To enable MIG, it's a little bit different than before. Now you're going to have to use the MIG manager. But again, you just go to the configuration of the MIG manager, and you specify which are the MIG devices that you want to use. In my case, I have an A100, so you can see that I have one MIG device 3G 20 GB and 2 MIG devices 2G 10 GB. If you sum them up, you'll see that I have 7G, which is how many compute units I have, and I have 40 GB of memory, which is my full memory. So I'm not wasting any resources. To actually enable MIG on the node, I have to go ahead and I have to label the node with the configuration I just created. With time slicing and MPS, it usually takes just a couple of seconds for it to kick in. With MIG, it will take up to a minute because a bunch of things need to be restarted in order for MIG to properly start. But once it does, you'll see that instead of the full GPU, you'll start seeing your MIG devices. So in terms of advantages for MIG, you have hardware isolation, which allows you to have processes that run independently for each other, and no one can influence anyone else. You have monitoring and telemetry at the partition level. And lastly, it's just flexible, because you can have smaller and bigger partitions based on your use case. From the disadvantages side, this is available usually for the fanciest and most expensive GPUs there are. Reconfiguring will require you to evict the already running processes, which can be a problem in production environments when you have a lot of users that are using the GPUs at the same time. And lastly, there is the potential loss of memory if you don't choose the partition layout correctly. But this is also a non-risk if you know what you're doing and you just choose the layout after careful consideration. So now we're going to use, again, use case number 1, 2, and 3. We're going to run them on the same GPU, but now with mix sharing instead of time slicing. So one thing you can immediately notice is that we have different colors per different processes. And this is because we have telemetry data for every partition, which helps debugging a lot. Secondly, every process is isolated. Every process is saturating its own resources, and processes cannot influence each other anymore. Also, you can see that the GPU utilization inside the partition is actually quite high, which is very good. So this is perfect, right? Yes, it is, because in this case, use case number 3 starved itself. You can see the line of the compute going down, while 1 and 2 just continued running without issues. So again, if we go back to our abstraction, we don't have the big fancy boat anymore. We have smaller boats, but every process has its own. And instead of evicting others, use case number 3 just evicted itself, while others could just continue blissfully enjoying the beautiful day. All right, so now let's see how our full system performs with GPU sharing. So again, we have our GPUs, but they're not full GPUs anymore. They're shared. And we're going to have smaller, medium, and bigger workloads. And we're going to try to schedule them accordingly. Now, the big one cannot go anywhere, but the smaller ones can. So we're going to go ahead. The big one will have to wait for a bit. So eventually, GPU is available, but it's shared. And in order to make it available to the big use case, we need to manually repartition. So we need to go to the node and change something so that the GPU is advertised as a full GPU. But once we do it, the big one can go there. If we have smaller ones and we need to share, again, it's a manual operation of going there and changing values so that our use case can run successfully. So there is a clear pain point, which is the manual reconfiguration that is required. So you either have to think in advance what is the best layout for your infrastructure, or you have to develop some kind of process that overlooks your cluster, sees what is trying to run on your cluster, and then tries to dynamically maybe change the layout that you have for your GPUs. But you can see that both options are far from ideal. Another clear pain point is just the configuration is per node. What this means, it means that if we decide to time slice, we need to go ahead and label our nodes, so all the GPUs that are connected to this node will be time sliced, even though maybe we wanted to time slice only one. The same happens with MIG. So if we decide on a certain MIG layout, and we go and label the node, all the GPUs on my node will be partitioned in the same way. And this is a problem because at CERN we have nodes that have 2, 4, 8 GPUs, and we want to be able to manage all of them individually. And with this in mind, let's dive in a little bit into DRA, or dynamic resource allocation. So this is an API to request and share resources between pods or containers inside a pod. This is a generalization that comes from the persistent volumes API, but for any generic resources. So if you use PVs, PVCs on Kubernetes, this will be pretty easy for you to understand. Very often, the resources that are managed with DRA is GPUs, but not only. It can be any device that attaches to your node. In terms of the feature state, this is already stable and enabled by default in Kubernetes 1.34. So to begin with, you need a DRA driver. And this is not something you're going to write yourself. This should be coming from the vendor where you have your hardware from. So since we have NVIDIA GPUs, we're going to have the DRA driver coming from NVIDIA as well. The DRA driver is publishing resource slices. And the resource slice is nothing else than just a representation of what devices you have available and attached on your node. After this, as a service administrator, you can define device classes. So what this means, it means that based on some criteria, you're gonna just categorize all the devices that you have into classes. And then as a user, you can create resource claims or resource claim templates to actually get access to those devices. So to make it a little bit easier, so the driver publishes something that looks like this. It's called a resource slice, and it's just all the information that you have available about your GPU. So the product name, the NVIDIA driver, the CUDA driver, and a bunch of other information. Then, as an administrator, you can create classes based on the information that comes from the resource slice. Lastly, as a user, you can either use the device class, or you can refer to fields directly from the resource slice to create a resource claim or a resource claim template. And then in the pod, you can reference, in this case, the resource claim template to get containers that are dividing the same GPU with time slicing. But this is much more complicated than it was before. So why do we want to use the array? And the very short answer is that it's very powerful. The longer answer is that before, we had to think in advance how to pre-configure the GPUs in our infrastructure. We had to also sometimes go and manually change the way we're sharing stuff to be able to fit certain use cases. And also, we had the per node configuration problem. With the array, we just have all our GPUs, all our hardware available on the cluster, and we don't have to manually do anything. And as a small pre-recorded demo, I will be running a couple of workloads on an A100. And I'm going to run a workload that has only one container that is using the GPU. And then we're going to run workloads that have a couple of containers and are using the GPU at the same time with time slicing or MPS. The main idea is that I'm not required to change anything. I can just create my workload, and then it will be scheduled, and it will work accordingly without me interfering or doing anything manually. So this is the output from NVIDIA SMI, and then I'm creating my first pod, which is just a pod with one container using the GPU. Nothing special, nothing fancy. Here it is running, awesome. But then I am creating a pod with two containers that are sharing the GPU with time slicing. And you can see both of them running, and I didn't have to do anything, any reconfiguration, any labeling, absolutely nothing. Just the GPU is available, the GPU was allocated to me. Now I can do the same with MPS. I'm going to have one pod with 3 containers that are accessing the same GPU with MPS. And you can see my NVIDIA CUDA MPS server, which is the daemon that manages the amount of memory and compute used by every MPS client. And then you can see the clients as well. And lastly, I'm gonna create a pod with 8 containers. And here you can see all of them coming up, and all of them running. Again, nothing else required than just creating a pod and the resource claim or the resource claim template. So how my full system will work with the array is just when there is a request, the GPU is just being shared. Nothing else is required. Now the big workload can go, no issue. But now, since we have a GPU that was shared into 4, but I have 3 workloads, it can just be dynamically reshaped to fit the new use case. So a couple of details to keep in mind with the array. So currently, a GPU can only be allocated to workloads that are located in the same namespace. And this is important because, for example, we at CERN use kubeflow, so every user has its own namespace. Secondly, dynamic allocation of MIG devices is not yet available, but it is on the roadmap. And lastly, using the NVIDIA array driver approach to access the GPUs will actually break the older way of doing things, so with spec containers, resources, limits. So it's not a big issue, but it's something to keep in mind. And if you want to find more about the NVIDIA array driver, please visit the link I put here. You can see more information about the roadmap, the plans, and the features that are already implemented. So now let's benchmark the new setup. we're going to use a Kubernetes 142 cluster. We're going to use an A140GB PCIe GPU, and the GPU access will be done with the array. And the first use case we're going to benchmark is called LQFT. So the atomic nuclei are held together by the strong force. And the strong force can be described by the theory of quantum chromodynamics, or QCD. Because of the probabilistic nature of quantum mechanics, you need to take into account all the possible ways the particles can interact with each other. And since there are infinite number of possibilities, this becomes intractable really, really fast. To solve this problem, space and time can be discretized into a four-dimensional grid. So you have three for space and one for time. And this is the input we're going to use for this use case. So basically, we can use NVIDIA CUDA platform to do calculations in QCD on GPUs. And this is why the project is called CUDA, because we're doing QCD on CUDA. And if you want to find more about the project, I linked it on the slide. The second use case we're going to analyze is called MLPF, or machine learning particle flow reconstruction. So when particles collide inside LHC, in the tunnel I showed in the beginning, new particles get created. And in high energy physics, or HAP, this is often referred to as an event. Now what we want to do is we want to be able to use state-of-the-art machine learning models and give as an input the particle tracks and the energy that we get from our calorimeters. And we want to get as an output the identity of the particles and their physics properties, like momentum, energy. And you can see a reconstructed particle in the image I put on the slide. So to begin with, we're going to run both use cases on a GPU, nothing interesting, nothing fancy, and the numbers on their own are not very interesting. Things become more interesting when we're going to run two processes at the same time on the same GPU, and we're going to do the sharing with time slicing. So you can see that the LQFT use case is doing great. We can do a lot of work in the same amount of time, and the fact that we're doing time slicing is not a problem at all. At the same time, MLPF is struggling. We can see that the performance went down. We can see that it takes a long time to run two processes, and in this case, the context switching is absolutely not negligible. If we go from 2 to 4 processes, this becomes even worse. But another thing I wanted to say here is that you can see that for input number 3, for LQFT, we're out of memory. And I didn't expect this to happen because I did my calculations and it was supposed to fit on my GPU. The problem is that a part of the memory is consumed to actually keep the state between the context switching. And this is what played nasty with me here because I didn't consider it. So that's why I'm out of memory. So this is something you need to consider as well. If we're trying to do MPS instead of time slicing, when we have two processes at the same time, both use cases are doing fine. It's looking good. But when we go from 2 to 4 processes, LQFT, which is the use case that was doing so great on time slicing, is struggling on MPS, and the other way around. MLPF, that was struggling before, is doing great with MPS. So why is it? Well, because in case of LQFT, it is affected by the memory bandwidth saturation, the cache thrashing, and in general, managing long-running kernels at the same time concurrently. And again, if you look at the input number 3 for LQFT, we're not out of memory anymore. And this is because with MPS, you don't have to do the context switching, so you don't have the extra memory that is consumed to keep the state, so we managed to run successfully. So a couple of conclusions for time slicing and MPS is the fact that whether or not you should use them depends heavily on your workload profile. And the only thing you can do is to benchmark and see how your script is performing with different sharing mechanisms. In general, MPS works great when you have a lot of idle resources because they can be used to run other processes in parallel. Time slicing makes more sense when you have bigger workloads because it avoids resource contention. But at the same time, time slicing can severely underperform if the process state is very complex, so it takes a very long time to actually perform the context switching. Now we're going to do the same thing but with MIG, and we will start with the LQFT use case. And you can see that we are out of memory for the bigger inputs on the smallest partition, which is 1G, 5GB. Also, you can see that we're going to double the amount of resources. So we go from 1G, 5GB to 2G, 10GB, which has 2 times the compute and 2 times the memory. And then again, we're going to double the amount of resources we have. And you can see that when we go from 1G, 5GB to 2G, 10GB, we almost get like no performance upgrade. We're almost running at the same amount of time. So I would argue that it doesn't make sense to actually do it because you use more resources, but you don't get anything back. At the same time, when we double the amount of resources again, we get almost 3 times the performance. So this is a clear indication that the LQFT use case can run greatly on bigger either partitions or maybe even a dedicated GPU, and this is something you need to check for. If we compare the same results on the MLPF use case, you can see that we're out of memory on the smallest partition. This was to be expected, but at the same time, the performance improvement when we are going from the 2G 10GB partition to 4G 20GB is actually maximum 141. So in this case, I would try to stay on 2G 10GB and use the leftover resources on something else. So a couple of MIG conclusions is that the smallest MIG partition is very often too small, so don't just go and divide your GPU into 7 instances to have a bigger offering. I don't think it will work. In general, request reasonably sized MIG partitions, or even consider a full dedicated GPU if you can make use of it. And lastly, MIG isolates the compute and the memory between the workloads. So this allows you to be a little bit more ignorant on what exactly you are running. At the same time, if you can spend the time and benchmark your use case a little bit, you can find the sweet spot where you're consuming the minimum amount of resources to get maximum performance. And lastly, just a note on monitoring GPUs. So since we're using primarily NVIDIA GPUs, we're using DCGM, or NVIDIA Data Center GPU Manager. Is just a tool that helps us get insights about the health of our GPU, the performance, the utilization, and also it allows us to change and enable custom metrics based on what exactly we want to monitor using field identifiers. If you use other hardware or accelerators from other vendors, then they for sure will have a solution for monitoring on their own. But just make sure you have detailed and very useful monitoring and telemetry data in your infrastructure, because it will save a lot of time in the future while debugging issues. And this is just an example dashboard that we have, that we published on Grafana Labs. It's accessible for everyone if you want to have a look. And it's just the MIG partitions that we have, the GPUs that we have, the utilization of the compute cores, tensor cores, memory, temperature, and just the basic stuff that you want to monitor on your GPUs. And a couple of final conclusions. So if you want to use GPUs and have the GPU access being done with DRA, it's not actually complicated. You just need to get used to the API. And the DRA approach in general is in active development, so try it out, get involved, provide feedback. This is always very useful. In general, different sharing mechanisms work best on different use cases. So try to understand the implications and choose accordingly. Consider using a full GPU when your use case can make use of it. And lastly, make sure you have detailed monitoring in your infrastructure. And to end with, this is a collision between 2 protons made of 3 quarks each. And a collision like this happens hundreds of millions of times per second in the LHC detectors. And I just thought it was interesting. Thank you very much for your attention.
Thank you very much, Diana, for this very insightful talk. We have time for questions from the audience. And we have a throw mic. I'm going to try that.
Thanks a lot for the talk. Why isn't it possible to share the GPUs across namespaces when using DRA? Where does the limitation come from?
From the driver. It's just the driver. Because In this case, you're using the exact driver that comes from NVIDIA. It's not a logic that was implemented from their side yet. And we actually pinged them and asked them about it, and they said it is possible, but it will require some changes, quite major changes in the code. But they know this is important, and it's on the roadmap.
Thanks.
Any further? There is one right up front here.
So thank you for the talk. You said in time slicing you're sharing basically the memory, so each process gets its part of the memory. Do you see this as a risk? Is there some security boundary, or can one process easily access memory from the other process? Have you thought about this? Or, is there some risk there?
So usually it is recommended to use time slicing with use cases that are in the same, let's say, family or team. So you can give access to a GPU to a team, and then they can run multiple processes that they all manage. I wouldn't use time slicing for completely different use cases across the teams. I don't know how easy it would be to access the memory for other process. I think it's possible, but it would be very hard. But the fact that processes can starve each other is probably my bigger concern, because this happens usually even before you get into the part where someone is trying to be nasty and access your memory. But I'm sure this is also a big concern.
Thank you.
Just behind you.
Thanks for the talk. If I understood correctly, for MIG, it's first in, first out, so you don't manipulate the queue handling, right? But with MPS, we have seen that some from later in the queue could jump because the bigger resource was available. So have you done some benchmarking with the queue management algorithm for MPS to see how far you need to go back to the queue to see who can jump in and who not?
No, we didn't benchmark this. This is a good point, but we didn't benchmark the actual queue of the MPS logic.
Okay, thank you.
Any further questions?
Do you combine it with Slurm or batch processing engines and stuff? Or
We're exploring it. We're not yet doing it. We've done a lot of usage of GPU sharing using queue and multi-queue. This is probably our primary focus right now.
Thanks.
Can you provide me some numbers about how many GPUs are you running in this context?
Yes, so in general, we have a lot of GPUs at CERN. I don't have the numbers. The problem is that they're all scattered around different experiments and different teams. So what we're trying to do now, we're just trying to centralize all of them. So actually the numbers are not necessarily impressive. We have less than 100 that we're centralizing right now. But yeah, the effort is to just grow the capacity based on the trust that we get of the users to start giving their GPUs that are dedicated by your team to our cause.
Okay, so are you going to have some, I don't know, Blackwell or how are they called, clusters?
I hope so.
There's one.
It's not out of the question.
Okay.
Right at the back, John and Noe.
Thanks a lot for the talk. Your user examples show that you've gone through a lot of pain with what people run on your GPUs. And I was just wondering, you've been analyzing what they do, but do you also do any feedback and training how they could optimize their workloads?
Yeah, so a lot of our users are people that are not necessarily very familiar with the infrastructures and the projects we're using right now. So we try to keep it as simple as possible for the users to use. In this case, we have Kubeflow as the entry point. And we do trainings where we explain okay, so this we cannot abstract away, so you need to learn maybe a little bit of YAML or a little bit of the basics. So also we try to do emails saying, hey, you allocated some resources that are idle for a couple of days, please do something about it. So there is a lot of communication back and forth. It's just, it takes a long time, and also some people just are not very willing to change. So we also need to take action from our side to help with it.
So you can optimize around, but there's certain hard boundaries.
Yeah,
where
we're
you can't
trying
get
both,
better.
basically.
Okay.
Yeah.
Thank you.
Thanks so much. CUDA is kind of a software mode, right, in this area. I'm wondering, do you see that a better hardware extraction will be providing different providers, say Huawei, AMD, a better leverage in this field because they're simply getting a better access to the underlying hardware without even having a better software abstraction?
I don't know. That's a complicated question. I think it can lead into a discussion like outside the talk. It's complicated to predict what exactly will happen because CUDA is so big that what I notice is that people are not willing to change to other vendors unless there is support for CUDA, actually. And then you start having all these interesting solutions to get CUDA to work on our GPUs. So I'm not sure if there will be something similar coming from our sides. I wish it would, because it's always interesting to see the development of different projects, and then I think this also is a very good opportunity for growth, but we'll see how it goes.
Thanks.
Any further questions for Diana? If not, let's give Diana another round of applause. Thank you.
Thank you very much.